Hello everyone, welcome back. I'm Kris, doing a couple of Thoughty 2s today. This is 124 light years away, something is waiting for us. Dun dun dun. Before we get started, it was a planet, by the way, I think. So in the thumbnail is what it looked like. It's just a big planet that has Welcome Earthlings sign with an arrow that's glowing. Alright, thumbs up if you could, subscribe to the channel if you like it. And then there's a thanks and the hype. Okay? I sound congested. My apologies. Let's go.
Hey, 42 here. Unless you've been living under a rock for the past few months, I don't blame you if you have. It's pretty wild out there. You've probably already heard about what might just be the greatest scientific discovery of all time. Using the most advanced telescope ever built by humans, the James Webb Space Telescope, a team of scientists from the University of Cambridge have detected a possible biosignature on a mysterious planet called K2-18b. That biosignature is a molecule called dimethyl sulfide, DMS for short, which scientists have detected floating around in K2-18b's atmosphere. That's pretty exciting news because on Earth, DMS is only produced in one way, by living things, predominantly marine phytoplankton. In other words, there's an excellent chance we just detected alien life for the first time. Or is there? It's important that we get this right because we aren't just talking about the possibility of aliens on a single planet here. If there really is life on K2-18b, it will completely change our understanding of the entire universe and our place within it. Located in the constellation Leo, K2-18b can be found 124 light years from Earth. On a human scale, that is a distance so vast it's beyond imagination. But on the scale of the universe, even the scale of our own galaxy, Earth and K2-18b are basically neighbours. If life in the universe is vanishingly rare, as some scientists suspect, the odds of finding two inhabited places so close together would be astronomically small. The equivalent of dropping 2 grains of sand at random anywhere on Earth, only to find them lying a few millimeters apart in the Sahara. If K2-18b is inhabited, it wouldn't just represent first contact, it would also be incredibly strong evidence that the universe is full of life, that Earth is just one amongst millions, perhaps billions of inhabited planets out there in the cosmos. So yeah, this is kind of a big deal. But as the late great Carl Sagan once said, extraordinary claims require extraordinary evidence. Which leads me to the question I'm going to answer in this video. Are the claims about K2-18b truly extraordinary? Have we finally found aliens, or is this just another false alarm? Let's find out. Today, we have a problem. We're drowning in distraction, we're overworked, stressed, and burning out. We rely on the wrong energy sources. Too often, people look for quick fixes like excess caffeine or sugary energy drinks, but there's a better, healthier solution. Magic Mind is the sponsor of today's video, and they sent me some of their shots to such a natural fierce lot who's right each, and there's no risk. K2-18b was first discovered in 2015 by the now retired exoplanet hunting Kepler Space Telescope. Despite technically orbiting its parent star in the habitable zone, at first it didn't look like the greatest candidate for possible biosignatures. It's simply too different to the only planet in the universe that we know for sure harbours life, ours. For one thing, at about 8.5 times the mass and 2.6 times the radius, it's much bigger. It's also much closer to its parent star, orbiting at a distance of just 0.15 astronomical units. Speaking of its parent star, that's very different to ours as well. Known as K2-18, it's a red dwarf, about half the size of the Sun, that produces just 2.5% of the Sun's total energy output. In the search for extraterrestrial life, we tend to focus our attention on planets similar to Earth, and it's fair to say K2-18b is anything but. However, in 2019, scientists made a discovery that changed everything. Water vapor in K2-18b's atmosphere. water vapor alone isn't considered a biosignature. We found it in all sorts of places that almost certainly do not harbor life. But this discovery was still a big deal, because it was the first time that water vapor had ever been found in the atmosphere of an exoplanet orbiting in a habitable zone. The 2019 study used data from the aging Hubble Space Telescope, and the detection was relatively faint and limited in resolution. But it was enough to convince NASA it might be worth pointing the soon-to-be-launched James Webb Telescope in K2-18b's direction. And in 2023, they did exactly that. And the results were intriguing. Whilst James Webb data did not definitively confirm the original water vapor detection, it did provide strong evidence for the presence of methane and carbon dioxide, as well as just the finest whiff of DMS, a potential biosignature. It was a groundbreaking find, but to begin with, nobody was all that excited. As was the case with water vapor back in 2019, the initial DMS detection was weak, with a statistical confidence of just 2 sigma, meaning the signal stood out from the noise by only 2 standard deviations. In practical terms, that left a 5% chance that the result was a random fluctuation rather than a real detection. But a follow-up study published earlier this year raised that confidence level to 3 sigma, meaning just a 0.3% chance that the signal was a statistical fluke. The study, published in the Astrophysical Journal Letters in April of this year, was extremely cautious about mentioning the A word. Astronomers usually are, because, at least so far, whenever they do, they've always been wrong. But Project Lead...
I'm going to say, if you're going to throw out aliens, then I think right off the bat, people aren't going to listen to what you're saying. The first thought is, oh, where's the life? Are they coming here? How far away is it? They're not thinking about anything else that's said. And if it's, it being wrong, it's never really been correct so far. The hypothesis of it could potentially is all we ever really hear.
Niku Madhusudan has been far more bullish. In a press briefing after publication, he describes the DMS detection as astounding and a revolutionary moment. In his words, these are the first hints we are seeing of an alien world that is possibly inhabited. Unsurprisingly, that kind of talk sent the entire international press into a first contact frenzy. But was it actually justified? Well, on the face of it, the logic chain seems extremely solid. The study found very strong evidence for DMS in the atmosphere of K2-18b, and DMS itself is extremely strong evidence of life. But all is not quite as it seems, and to understand why, we need to delve into the cutting-edge science behind this potentially paradigm-shifting discovery. So, first things first, how did we figure out what's in the atmosphere of a planet located 730 trillion miles from Earth in the first place? Well, whenever a planet passes directly between its parent star and one of our telescopes, we witness a slight dip in the star's luminosity. Monitoring for these tiny cosmic blinks is called transit photometry, and it's how the Kepler Space Telescope found K2-18b in the first place. But with telescopes as advanced as James Webb, we're able to go one step further. Picture a typical planetary transit. From our perspective, here on Earth, most of the light hitting the planet is simply blocked, but a tiny sliver of that light will pass right through the planet's atmosphere, if it has one, before continuing on its merry way to Earth. And by analysing the atmosphere-filtered starlight, a technique called transit spectroscopy, we can learn a lot about the molecules it interacted with on its journey. Well, that's the theory, anyway. But there's a catch. Transit spectroscopy is really bloody hard. For one thing, we're only interested in a truly tiny fraction of the total light output of the star, just a bit that travelled directly through the exoplanet's atmosphere. That means, before we can even get started with the analysis, we have to tease out a minuscule signal from almost overwhelming noise. If we do that properly, we end up with something like this, a kind of barcode of light wavelengths known as a spectrum. Different molecules in a planet's atmosphere will absorb light at different wavelengths. So, by reading the dips in the barcode the missing light, so to speak, we can figure out which molecules are likely to have been responsible. Unfortunately, this is where the barcode analogy falls flat on its arse, because interpreting light spectra is nowhere near as simple as just scanning a barcode. Atmospheric conditions can alter our signal in various ways, muting, masking, or shifting aspects of the spectrum. It's all very complicated, but for our purposes, all we really need to know is this. In order to accurately read the spectrum, we must understand certain things about our exoplanet's exoatmosphere. For example, how much cloud cover or haze there is, and what the temperature and pressure gradients look like. So, how do we know these parameters for K2-18b? The answer is, we don't. Scientists get around this problem using advanced computer modeling, simulating thousands of potential atmospheres based on our best guesses of the conditions on a given planet. And for each of these simulated atmospheres, the model generates a synthetic spectrum and compares it to the real one captured by the telescope to find the closest match. It's an ingenious solution to a truly tricky problem. The trouble is, atmospheres are incredibly complicated, and there are so many variables to consider we could never simulate all of them. Instead, we have to make some assumptions. And this is where things start to go wrong.
Yeah, you have to make assumptions about a planet that's 730 trillion miles away, 124 light years. We're making assumptions about almost everything we see because we have no ability to get there to find out. So you don't have to explain that we're making assumptions. We all understand.
The 2025 study that made headlines around the world focused its analysis on the key assumption that K2-18b is a so-called Hycean world, an ocean planet with a hydrogen-rich atmosphere. It used atmospheric parameters consistent with such a planet, and it tested for gases that we would expect to find there. That isn't necessarily wrong. The Hycean world hypothesis broadly fits the data we have on K2-18b, but it isn't the only scenario that does. Some scientists believe K2-18b is more likely to be a magma world covered in an ocean of molten rock. Others that it's a mini Neptune with no distinct surface at all. The fact all three of these wildly different scenarios are still on the table shows how little we really know about this distant world. More importantly, such dramatically different atmospheric conditions would each have completely different spectra for a given set of molecules. That impressive sounding 3 sigma confidence level for the detection of DMS is only actually valid if the team's initial assumptions are correct, and many scientists think they aren't. A couple of weeks after the publication of the bombshell paper, a physicist from Oxford University reanalyzed the spectral data using a different model with different assumptions and concluded that there was no evidence for DMS whatsoever. The fact that two different teams of scientists can take exactly the same data and come up with completely different results is a pretty good indicator of just how tricky transit spectroscopy really is, at least for now. This is science at the very limit of both our current tools and our understanding of many of the concepts involved. But, for the sake of argument, let's just say there really is DMS in K2-18b's atmosphere. Well, it turns out it might not even matter. DMS has long been considered an excellent biosignature candidate because it is exclusively produced by living things here on Earth. But in recent years, we've started finding it in places where we know for certain living things can't have made it. In 2024, scientists detected DMS in the tail of a comet in our very own solar system. And it goes without saying that this barren hunk of ice and dust has no atmosphere, no oceans, and no biology. And yet, thanks to some currently unknown abiotic process, it harbors a so-called biosignature. So, if we know it can be produced abiotically, even if there is DMS on K2-18b, how can we be certain it was made by living organisms? Well, we can't. The more we learn about life, the universe, and everything, the more scientists are starting to suspect the idea of finding a single silver bullet biosignature maybe a little optimistic. As is the case with DMS, just because a molecule is only produced by life here on Earth, it's hard to say for sure it can't be produced abiotically elsewhere in our universe. The universe is big, and there's lots of weird shit going on that we don't really understand very well, particularly on exoplanets that are very different to Earth. To convince the wider scientific community that a planet is inhabited, we may need to dig a little deeper and build a kind of case for life. For example, we could search not just for a specific biosignature gas, but also for seasonal atmospheric variations that might hint at underlying biological rhythms. Or we could try to combine biosignatures with technosignatures, like evidence of pollution or the presence of synthetic chemicals. It's a bit more complicated, all that, possibly beyond our current technology, but it would be a lot more convincing. Okay, so where does all of this leave us with K2-18b? Well, for now, at least in my opinion, there's a good chance, an extremely good chance, that there isn't life on this distant world. The DMS detection is based on shaky assumptions, and even if it's actually there, we can't be certain it was produced by life. But these results do give us a strong incentive to keep studying K2-18b. It's very likely to be another false alarm, but it's an interesting planet nonetheless. And the only way to be certain, one way or the other, is to gather more data. It's also a pretty great candidate for study in general, thanks to its tight orbit. A year on K2-18b lasts just 33 days. That means there's a new transit to analyze about once a month. All that data could prove incredibly valuable. Transit spectroscopy is a relatively young and rapidly evolving technique, and the more practice we get, the more we'll learn. That can only be a good thing. After all, we want to make sure we're ready if we ever do point our telescopes at a planet that harbors life. Thanks for watching.
It's nice that, that we're, how am I trying to phrase this? The habitable zone. It doesn't sound right. Anyways, it makes sense if we're looking for life such as ourselves, but we don't know what kind of life there is out there, as opposed to what habitable zone it needs. So when we look for planets in the area that we know that we could live, we could survive, that makes sense. But it's also difficult because not all life needs what we needed to survive. We could be missing so much, and at the same time, maybe not. But it's 124 light years away. Studying, it's fine. But as the universe is expanding, it's only going to get further away. So, basically it's a pipe dream if people think that they're going to leave here and go live somewhere else. It's not working. It's not going to happen. But it's always interesting to see, because the aliens are coming from somewhere. Well, I hope you enjoyed. I did. And until next time, have a good day. Have a good night.